We type these four simple letters all the time. JOIN. It just works. It feels instantaneous, almost like magic. But behind that one little word, there's this entire world of complex decisions and, honestly, brilliant algorithms that decide if your query is going to fly or just completely fall on its face. So today, we're going to pull back that curtain on the SQL join.
And yeah, this quote really gets to the heart of it. That one key word kicks off a whole process where your database's query planner has to make a choice. You got to think of it like a master craftsperson, right? They've got a whole toolbox full of different ways to join data. And picking the right tool for the job, it's everything.
Because we're not talking about a small difference here. The gap between a good choice and a bad choice is massive. We're literally talking about a query that runs in milliseconds versus one that just sits there grinding away for minutes, maybe even hours. The stakes are just incredibly high.
So what makes it so hard? Well, the most obvious way to do it, the naive approach, would be to just compare every single row from the first table with every single row from the second. But look at this number. If you've got two tables with 1 million rows each, that's 1 trillion comparisons. 1 trillion. That's not just slow, it's totally impossible for any real application. Databases have got to be way, way smarter than that.
Okay, so let's start with the most basic kind of brute force approach. It's the one we'd all probably invent first if we were building a database from scratch. And that's the nested loop join.
The idea here is, well, brutally simple. It really is just two loops, one nested right inside the other. You grab one row from your first table, the outer table, and then you scan the entire second table from top to bottom looking for a match.
And you see that third step? Repeat? That's where the pain comes from. If your outer table has 1 million rows, guess what? You're repeating that full scan of the inner table 1 million times. This is that O(n) times m complexity we talked about, that trillion comparison nightmare.
But you know what? The real killer isn't even the number of comparisons. It's the I/O. It's reading from the disk. See, if the outer table is small, you only scan that inner table a few times, and it probably just stays in the super fast memory cache. But if the outer table is large, you're constantly having to reread the inner table from the slow physical disk over and over and over again. This is exactly why query planners always try to put the smaller table on the outside.
So the whole game becomes, how do we reduce the number of times we have to scan that inner table? The block nested loop join is a pretty clever optimization for this. Instead of taking just one row at a time from the outer table, it grabs a whole chunk of them, a block, holds them in memory, and then does one single scan of the inner table to find matches for that entire block. It's a huge, huge improvement.
But we can do even better. For most large joins where we're just checking for equality, where this ID equals that ID, modern databases have a much more powerful tool in their toolbox, the hash join.
The idea here is absolutely genius. Instead of scanning over and over again, you just do 2 passes over the data. That's it. First, you take the smaller of the 2 tables and build a super fast lookup structure in memory, a hash table. Then, you just walk through the larger table one time, using that hash table to find any matches almost instantly. This brings the complexity way down to O(n) plus m, which is a total game changer for big data.
And these 2 phases are the heart of the whole thing. Phase 1, the build phase, is all about getting ready, creating that hash table. Phase 2, the probe phase, is the actual work, using that hash table to find all our joined rows. It's clean, it's efficient, and it is incredibly fast.
Now, it's not a silver bullet. It's amazing for large equality joins, but it has one huge weakness. That build table, the smaller one, must fit in your computer's memory. If your smaller table is still too big for your available RAM, the whole strategy just falls apart. It also doesn't work for non-equality joins, like when you're looking for a range of values where one thing is greater than another.
So what happens if we can't use a hash join? Or what if our data already has some really useful structure that we can take advantage of? Well, this brings us to a couple of specialized, very clever algorithms.
So, first, let's just ask a simple question. What if both of our tables just happen to be perfectly sorted on the exact key we want to join them on?
Well, if they are, we can use a sort-merge join. And honestly, the best way to think about this is like a zipper. You just walk down both sorted lists at the same time, merging them together in one single beautiful pass. It's incredibly efficient, and it doesn't have that big memory requirement of a hash join. The only catch, of course, is that the data has to be sorted first.
Okay, different scenario. What if our data isn't sorted, but what if we have an index on one of the tables?
This is where the index join comes in.
You can think of it as a super-powered nested loop. For each row in the outer table, instead of scanning the entire inner table, it just uses the index to do a lightning-fast lookup. It basically turns that slow, painful scan into a precise, targeted seek operation, which is worlds faster.
All right, so we've covered the main algorithms that work on a single machine. But what happens when the data gets truly massive? I'm talking so big it can't even fit in memory anymore, or it's spread out across a whole cluster of computers.
Remember that big memory problem with the hash join? The Grace hash join is the answer. It's a two-stage process. First, it smartly chops both of your big tables into smaller, more manageable chunks, or partitions, on the disk. Then, it just performs a regular in-memory hash join on each pair of partitions one by one. It's the heavy-duty version for when your data spills way over your RAM capacity.
And in the distributed world, with systems like Spark or BigQuery, we have the broadcast join. The idea is, if one of your tables is small enough, the system just sends a full copy of it to every single computer in the cluster. Then, each computer can join its local piece of the giant table without having to send massive amounts of data back and forth across the network.
The key insight here is all about avoiding something called the shuffle. Shuffling means taking both of your huge tables and redistributing them across the network so that all the matching keys end up on the same machine, and it is incredibly expensive. Broadcasting a small table is just way cheaper than shuffling a massive one. That's why this strategy is a huge win when you have a big table being joined to a much smaller one.
So we've got this whole toolbox, right? Nested loops, hashes, merges, broadcasts. How on earth does the database actually pick one? Well, that is the job of the query planner. The planner is basically a cost-based optimizer. It looks at everything it can. How big the tables are, what we call cardinality, how much memory it has to work with, whether you've got indexes or sorted data, and it estimates the cost of using each possible join algorithm. Then it just picks the one that it calculates will be the cheapest and fastest. Simple as that.
So all of this incredible complexity, partitioning, hashing, sorting, broadcasting, it all just happens automatically, hidden behind those 4 simple letters. It's a really fantastic piece of engineering. So the next time you write a join, maybe just take a second to appreciate the silent, critical decision your database is making for you. Will you think about which tool it's choosing from its toolbox?